Welcome everyone. It looks like this week I decided not to publicize CFA-wide at the ITC Lunch, and it seems to work. We are not over-flooded, so we'll keep it this way. We just had an excellent colloquium by Chung-Pei, who told us about the 100 most massive galaxies within 100 megaparsec. And she will tell us a little more about their innermost content in terms of supermassive black holes in a few minutes. And then we'll hear from a newcomer to the ITC, John Forbes, that will tell us why do dwarf galaxies form stars so slowly. And we published a paper in Nature several months ago related to that. And then we'll hear from Anna Mosquera, who is visiting the CFA, somewhere over there. And she will tell us about baryonic acoustic oscillations in neutral gas observations with a survey called BINGO. And that is a novel single dish experiment. Then finally we'll hear from a visitor from outside, from another continent, the Weizmann Institute, Barak, Zackay, over there. And he will tell us about detecting pulsars in tight binary systems using observations with integration times longer than an orbital period.
Okay. Thank you. I'd like to give an update on supermassive black holes beyond M87, both in terms of distances and in terms of mass. So this sigma relation, which had been very influential, first established in the 2000s by different groups, showing that the black hole mass over 4.5 decks of mass is shown here versus some host galaxy properties. Doesn't really matter what you show here. This one is the velocity dispersion of the stars in the host galaxies. You could use the bulge mass, you could use the bulge luminosities. Basically, the bigger the galaxy is, the more massive the black hole is. And this relation, I don't want to go into the relations here today, but this relation has been used in many demographic studies of black holes and galaxy formation and coevolution assembly, and for predicting many properties of black holes as a population using the sigma. But today I would like to focus on the very upper right end here in the 10 billion solar mass range for the black hole mass. And here you see three galaxies, M87, which had been a record holder for 3 decades before 2011. In 2011, we reported the discoveries of two 10 billion solar mass black holes. Both are in rich clusters. NGC 4089 is the brightest cluster galaxy in the Coma cluster, and NGC 3842 is the brightest cluster galaxy in the Leo cluster. So today I'd like to give you some updates on what's happening at the very high end. So again, just a few properties of these three galaxies I just talked about. You can see that the masses are now going beyond 10 billion solar masses for the black holes. But these three are all very quite prominent clusters on the sky, northern sky. And these are all dominant, the sort of anchoring, these are the galaxies anchoring the potential of the clusters. And earlier this year, we reported the discovery of a 17 billion solar mass black hole in the galaxy NGC 1600, which was targeted as part of the massive survey I spoke about earlier that studied systematically the 100 most massive galaxies within a distance of 108 megaparsecs. So we targeted this galaxy, and it is obviously a massive in stellar mass, a galaxy not quite nearly as massive as 4089, but what's striking about this galaxy is it's in a fairly normal wimpy group. It's not a gigantic cluster like the Coma cluster or the Virgo cluster. And it's at a distance a little closer at 64 megaparsecs. And so I'll show you the environment momentarily. And we are working on now the twin of Coma cluster, the NGC 4874. So this is the second brightest galaxy in the Coma cluster. And now we have preliminary mass, black hole mass measurements of 11 billion solar masses. We're still running many short orbit models to pin down the error bars here. Our data look pretty good. So I would just compare these diverse environments lived by these most massive black holes. Here is the figure we had in our Nature paper comparing the NGC 1600 group to that of Coma cluster. Both are shown to 500 kiloparsec on a size, so this is a very fair comparison of physical sizes. And the Coma cluster, of course, has the remarkable 4889, and its twin is just a little bit dimmer, but you can see two very large, massive galaxies, early type galaxies anchoring its potential here. NGC 1600, by contrast, it outshines its neighbors by at least factor of 3, and it's in the group. Its virial mass is probably about 10 times lower than that of Coma, the Coma cluster. Its X-ray luminosities is at least 1,000 times lower, and the rank 2, the second brightest galaxy in this cluster, is at least 3 times fainter. So this is almost like a fossil group in contrast to the Coma cluster. And the distance is about 50% closer. And the one we are working on right now, the twin of 4889 is 4874. This one is even more painful to study because it has almost no light at the center. As I will show you momentarily, it has very diffuse stellar core. And you can see these are very massive galaxies in stellar masses, and velocity dispersions are quite different for the two galaxies. So they're going to sit on different parts of the M sigma relation, and this is the core radius I'll talk about next. Okay. And so adding on to this plot I just showed now, B1600, and the one we're in preparation, 4874. So you can now see these dots are global fits to either the total population early type is shown in the red, late type is shown in blue, and black is a fit to the total sample here. Again, over many orders of magnitude in black hole mass. So you may want to ask, is sigma a good predictor for the black hole mass? This time-honored sigma people love to use to estimate the black hole mass seems not to be working so well. That is to say, the black holes we are finding right now are all above that predicted by the sigma. And our spatial resolution, because these black holes are so big, their sphere of influences are really big, so we don't worry about not resolving the smaller ones. To put it another way, if there are more of these black holes out there, we should be finding them. We can find them. We have the angular resolution to find them. So this is not, we don't think it's a particularly a selection effect or anything. Just somehow these black holes are more massive. Another way to say it is there are very few galaxies beyond sort of 350, 400 kilometers per second. The galaxies sigma just sort of top out here. The black hole masses seem to, that they can grow more. The other well-known correlation between the black hole mass, so the y-axis is the same as the previous plot, is the versus the bulge mass, stellar bulge mass of the host galaxy. And here we're only plotting the early types because we don't want to bother with the disk bulge decomposition, which is very tricky, and typically people only plot the early types here. And again, you can see that our the two black holes we're publishing this year are above the relation. In fact, 1600 is about 10 times above the relation. The mean is about, the black hole is about 0.2% of the host galaxy bulge mass. For 1600, it's about 2% for the black hole mass to the bulge mass ratio. Okay, so it will be nice to understand what's going on in this regime better, because these are the biggest black holes. They will probably give the biggest, event horizon size, and probably angular size-wise will be big too if they're closer, so there will be good targets for the event horizon telescopes, and also for pulsar timing arrays that are looking for gravitational radiations from binaries, if these are in binaries. So we would like to understand these better. So a new sort of relationship we published in this earlier this paper, in the same paper in which we reported the black hole mass of NGC 1600, is the property of the core of these galaxies. This is just the surface brightness of the stars versus the radius for a bunch of elliptical galaxies here. The blue ones in the background sort of run-of-the-mill, nice HST images of the vocal lore, cuspy profiles. This is surface brightness in solar luminosities per parsec squared. And I highlighted these biggest ones I just talked about. You can see they characteristically turn over. That is to say, the actual physical density of stars are lower in these giant elliptical galaxies, ironically. Okay. But the outer part obviously are brighter, so their total luminosities are brighter, but near the core, here I'm talking about within about 1 kiloparsecs, they flatten. So you can compute, you can fit to the core radius. The core size clearly is indicating some physics happening here. And because they are flattened, there's so little light here, people used to target black holes with smartly, they target these black holes. These are much easier to study because you can get enough signal to noise for the spectrum. So, and people used to use the HST for the angular resolution. Our strategy had been to, in order to study these, we really need 8 to 10 meter ground-based telescopes, but we still need fantastic seeing. So we use either adaptive optics or natural seeing, but at about 0.4 arc seconds or so, which can actually resolve these spheres of influences here. Okay, again, I don't want to go into details of the origin of the core. I think that by itself is a very interesting question. One running candidate is maybe binary core scouring, black hole kicking out stars on radial orbits through slingshots can get rid of these stars. Okay, and I think AGN feedback is another way to explain why these galaxies have such diffuse core. Okay, but I think these measurements will help constrain these different models. So now I can characterize these cores using either core Sirsic profile or Nuker profile. We tried both of these. Okay, and here is a plot. Again, the x-axis is the core size, so that's just based on photometry. HST in this case, it had nothing to do with the black hole. It's just where this light bends over for the stars. And the y-axis now is the sphere of influence of the black hole. So this is a sample of cored galaxies that have dynamically measured black hole mass. So it's a subsample of the 80 plus that I show you on the M sigma relation. But since these are done by various groups, some of these are by us, and since we know the exact modeling through the short orbit modeling for the stellar profile, the black hole mass, and the dark matter, so we can actually compute the radius at which the black hole mass equals the enclosed stellar mass, and that's the definition of the sphere influence. And that's plotted in the y-axis. So y-axis has a very strong, it's reflecting the black hole's influence. X-axis is just a light profile. And I think I've shown this last year that this is a 1-to-1 fit. So that is to say, our sphere of influence is statistically equivalent to the core radius, and with a very tight scatter of 0.17 DAG within these 21 galaxies. So this is probably the tightest correlation we have seen for a black hole property versus the galaxy property. And to put it another way, for these big galaxies, sigma is no longer the good proxy for black hole mass, but I think core radius, and core radius you can get just based on photometry alone, you don't need spectroscopy, is a much better indicator for the black hole mass. Okay, so changing the y-axis rather than the sphere of influence radius, this plot is radius versus radius. Okay, but we also have the black holes, so you can contrast this black hole versus core radius with M sigma or M bulge relation I showed earlier. Again, this is just a subsample of the galaxies that have cores, and this is over a much smaller 2.5 DAG in black hole masses. You can see these are all very massive, and this relation, again, you can see is much tighter than M sigma relation in this regime, and this is our yet to be published 4874. Okay, another way to put it is if I can measure the core radius based on photometry, HST photometry, now it opened up the channel for predicting black hole masses. And of course, we can follow up with the spectroscopic dynamical measurements to confirm. So I would like to add a lot more points to this plot, and our search strategy right now is to now not looking at sigma, but looking at core radius. So in summary, there is a new population of supermassive black holes beyond M87, which is at 6 billion solar masses, and these are all beyond the Virgo cluster at a 16.7 megaparsecs, and you need to go beyond that to find big galaxies and big black holes, and this will provide candidates for the Event Horizon telescopes and gravitational wave searches at a nanohertz regime targeted by the pulsar timing arrays. And I highlighted sort of the environment. Not all these big black holes live in the richest clusters. And again, the massive survey will allow us to study these systematically because we are not selecting based on environments. And NGC 1600 is the first example of a very extreme black hole outside of a rich environment. And I talked about these relations not working anymore at a high mass end, but luckily we may have a better relation here. And this not only are the two radii proportional to each other, the intercept is statistically consistent with 1. So these two radii seem to be really reflecting each other. So that is to say, the core is probably very likely caused by the black hole. Okay, so the new hunting strategy to increase the population forward to even larger population is to combine the massive survey with HST photometry, which we're analyzing right now, to look for large cores, measure the cores, infer the black hole mass, and follow up with AO spectroscopy. Thank you.
The highest masses that you're finding are very similar to the highest masses of quasars if you apply the Eddington limit by the velocity function. It seems like since redshift 6 to the present time, the upper envelope of the black hole mass function is pretty much set at a few times 10 to the 10 solar masses. Do you have a conjecture? Why is that?
That's right. So the uncertainties are pretty big, but you can now start to ask about the number densities. And within the big uncertainties, it's fairly comparable. So it seems to indicate that some of these black holes may not have grown so much. They need to be the sort of the sigma peak, sigma peak. They're the most voracious objects in that high gas-rich universe, but once they swallow up and then form these black holes, it seems like they are fairly quiescent. That may be one indication. Another corollary of this is people have looked at luminous quasars. Where do they live at high redshifts? What environments do they live? Based on correlation calculations, they have the paper saying that most luminous quasars do not necessarily reside in the most dense regions in the high universe. And I think NGC 1600 will be supporting that, in that even locally, the most black holes do not live in the densest, do not necessarily have to live in the densest regions.
So it seems like what ruins the M-sigma relation is that you just don't have galaxies at very high sigma. Right? If you had galaxies that were in 1,000 kilometers per second velocity dispersion in principle, the black holes would be on the relationship. So do you have a sense of what mechanism might truncate velocity dispersion to be no higher than roughly 500 kilometers per second?
Right. So in fact, I started studying these black holes based on about 10 years ago when Mike Boyle and Colchin, my student then, we were actually studying simulations, merging the elliptical galaxies to form bigger ellipticals. That's when we saw in the simulations that the M-sigma relation is saturated. And that's how I got into this observational effort here. And there, the reason is when you merge two galaxies, sigmas actually don't change so much. The stars scramble, you gain a little bit. The black holes, if they can merge, they add. Okay, so this is this dry merger regime where it's actually not, it's fairly natural for that to happen. Another comment is the sigma is a sigma of the galaxies themselves. We do have groups and clusters where the members, right, the sigmas can go out to 1,000. So some people have proposed maybe if you use you plot a different sigma, you may be able to stretch out that part. Okay, that's another thing to investigate.
So the M87 mass is controversial, it's very meaningful. But for the HT, for example, your methods of determining the mass, are they different than the methods that have been used to get the masses for M87 from the two groups? And have you looked at the M87 data? In other words, what would you say the mass of M87 is if you worked your algorithms on it?
Right, so our method is the same in terms of the tracer. So we're using, as I highlighted, there are masers. You can't see black holes, so obviously you got to look at luminous stuff, measure their velocities. And there are currently 4 tracers. Masers, most beautiful, and people here work on that. Unfortunately, they don't seem to correlate with the galaxies so well. These galaxies often don't have a bulge even. And ionized gas is the lower mass measurement for M87, and the higher, the 6 billion, is based on stellar kinematics. And our method is to use stellar kinematics, which I think is the cleanest, short of masers. Most of these galaxies don't have masers. So ours is the same as the 6 billion solar mass measurements. So there is a systematic, so each measurement has small error bars, but it's a systematic between the ionized gas and the stellar mass measurements for M87 that's still yet to be resolved. And we don't have, a lot of these don't have ionized gas close enough for us to do this comparison. But we have also CO data for some of these. So I think very few of these black holes have multiple tracers. Okay, 4258, for example, the beautiful first maser black hole, the stellar kinematic measurement agree very well with the maser black hole masses.
So at the high mass end, when you see this enormous range in black hole properties like fixed sigma, does that range in black hole properties correlate with other things like V over sigma or population properties or anything else?
Yeah, so far what we see is the core radius. That seems to really be the tightest. And you saw with the bulge mass, it doesn't seem to correlate so well either. I think the sample is too small to do a detail, to look for other, it doesn't seem to correlate with color or gradients or anything so far. Yeah, I think finding more will help us find other axes to correlate with.
Just before we let you leave the podium, I wanted to mention that this is a theory forum here. And Chung-Pei is an inspiration to many of us. She started as a living theorist, and now she's a living observer. And perhaps there is only one person in the room sitting next to me that did that. But it's a very rare path. It's a very rare path, and we salute you for seeing the light. So.
Thank you.
All right. Hi, everyone. So I just started here at the ITC, so thank you all for being here. And I wanted to talk today about a project I did as a PhD student with my old advisor, Mark Krumholtz. And spoiler alert, this is a talk about a simulation. The question I want to answer is, why is the depletion time so long in dwarf galaxies? And so let me start out by showing you some data. And the point I want to get across in this slide is that dwarf galaxies form stars extremely slowly. And the quantity I'm going to use to quantify this is this thing here, the depletion time. And the depletion time is just the ratio of the gas mass to the star formation rate. It tells you how quickly or how long it will take a galaxy to burn through its current gas supply at its current star formation rate. And to give you an idea, the Milky Way has a depletion time of a few gig years. But if you look at a sample of nearby dwarf galaxies in the field, you see that the depletion times there can be substantially longer, definitely exceeding the age of the universe and even approaching 100 gig years. So the question is, why do these galaxies form stars so slowly? And I'd say that there are two main camps on this issue. One is supernovae. So supernovae have long been thought for decades to be especially important in dwarf galaxies, and that's because dwarfs are small, they have shallow potential wells, and so supernovae should have an easy time moving gas around in these galaxies. And there's a whole class of models where supernovae are responsible for regulating star formation. You form exactly enough stars to create enough supernovae to keep turbulence going to support the ISM. So that's one set of models. Another set of models relies broadly on interstellar radiation. So, and these models basically work by regulating how much cold gas there is available for star formation. So to look into which of these two mechanisms, which of these two sorts of models are more reasonable in dwarf galaxies, we decided to run a numerical experiment. So what we did is we created an isolated galaxy, put it in a box, simulated it with ENSO. We started it with 10 to the 7 solar masses in stars and 10 to the 8 solar masses in gas. So it lies on this relation for stellar mass versus gas fraction, basically. And then what we did is we just flipped two switches. We had two switches. We turned supernovae on and off, and we turned photoelectric heating on and off. Photoelectric heating, which I'll talk about more in a second, is basically one of the primary channels by which interstellar radiation acts on the gas. Okay, so what is photoelectric heating? So photoelectric heating is just the ionization of dust grains. So you have young stars that generate photons with a variety of energies. Those above 13.6 eV will ionize hydrogen, and that means they don't get very far typically in a galaxy. But these photons between 8 and 13.6 eV have enough energy to travel, have low enough energy that they are able to get past all the hydrogen, and in fact, the galaxies I'm considering are basically optically thin to this radiation. So they travel throughout the galaxy. They may eventually hit a dust grain. When they do, they have plenty of energy to ionize it. That electron then shares its energy with the surrounding gas. And people who study the ISM have known that this is a very important process for a long time. So this is a model of the ISM near the Milky Way, or near the solar circle, rather. And these lines show you various heating and cooling rates as a function of density. And you can see that if you look at the heating rates, photoelectric heating is totally dominant over this entire density regime. But it's been sort of deemed unimportant for the star formation rate in Milky Way mass simulations, and it's also not really commonly included in galaxy simulations, and part of that's because we've only relatively recently started really trying to simulate the ISM in great detail in large-scale galaxy simulations. The other piece of this model is supernovae, and supernovae are very tricky to simulate because if they go off in gas which is too dense, so this is a CDF of density in the simulation, if they go off in gas which is too dense, then the supernova remnant will cool quickly and you can't resolve it so it won't expand very far and you can't resolve it in your simulation. But because we're dealing with dwarf galaxies, which are physically smaller, which have lower densities in general in their ISM and have lower metallicities, we actually end up with all of our supernovae, which is this red curve here. All of them are to the left of this line where we think they're basically resolved. And if you look very closely, you can see individual supernovae actually going off in the simulation, sort of like popcorn or lightning bugs. So what's the result here? So this is the first thing you can do. You can plot the star formation rate as a function of time for the 4 different cases where each of these is on and off. So let's start with the black line where everything is on. That's what we think the real universe should be. And you see that the star formation rate rises and then levels off around 10 to the minus 3 solar masses per year. When we turn off supernovae, we get the red line, and you'll notice that it's not very different. Whereas if we turn off photoelectric heating, you get the blue line, and the star formation rate is 5 times higher. So what that tells us is that actually it's not supernovae, but more photoelectric heating, which is determining the star formation rate in these galaxies. Next, I'm going to say something which might surprise you, which is that in our original paper, the simulations were not perfect. So actually the plot I just showed you is from a new set of simulations where we've fixed a bunch of issues with the old ones, and the effect is a bit smaller, but it's still there qualitatively. So to understand this result, one thing we can do is look at what the photoelectric heating field is actually doing in this simulation. And here are a few snapshots showing that. And you can see that we're actually resolving the photoelectric heating sources into individual sources, and each of these varies in time and, of course, space. And so the photoelectric heating field across the galaxy can actually vary by a huge amount. So treating it as sort of constant in space is not a great approximation, but lots of people do that. But why does it make such a big difference, whereas supernovae actually don't seem to make much of a difference? And to answer that, let me show you the gas in the simulation as a function of density and temperature. You can see, well, let me orient you a little bit more. This black line here is where we allow stars to form in the simulation, because this is the gas which is unstable on the finest resolution elements that we're resolving. And you can see that in the fiducial simulation, when gas gets this cold, it doesn't stay there for very long. It's quickly heated back up to near the threshold or above. Whereas, I can play it again, if you only have supernovae, because supernovae have some delay before they go off, and because they only affect a very local area, whereas the photoelectric heating can affect sort of wide swaths of the galaxy, you end up in the supernova-only case with lots and lots of cold, dense gas, which is where all the star formation is coming from. Okay, so to conclude, supernovae are subdominant in setting the long depletion times of dwarf galaxies, and in fact it's photoelectric heating which is doing it. Photoelectric heating can vary by orders of magnitude across a galaxy in space and time, so don't treat it as constant. And I'd also like to invite you to ask me for any of this data. The old simulations are public, but I haven't had a chance to put these up yet, but I'm happy to share this data if you have any applications in mind. So, thank you. Yeah. That's true. So at high redshift, I don't expect this to work very well. Yeah. So and certainly it will also start mattering less and less as you go to massive galaxies, because more and more self-shielding comes into play, and the dwarfs are not optically thin anymore to this radiation.
So some of the dwarfs may have had high stuff to start with, but then.
Yeah, that's possible.
So I seem to remember authors speaking of the depletion time in terms of the total molecular gas over the star formation rate. And it seems like that would be a better diagnostic, but it looks like you're plotting the total atomic hydrogen. So can you explain why you did that, and if using the molecular mass would bring dwarfs more in alignment with larger galaxies?
Right. Yeah, it's certainly the case that if you only look at the molecular depletion time, you get a much more sort of constant value of the molecular depletion time, and basically that's why this sort of model is very popular, because the interstellar radiation tells you how much molecular gas you actually get. So these models are all about how you, or at least this one and this one, are about how you calculate the molecular fraction. So what we're simulating here is, what we're basically verifying is that, in fact, it is the cold gas content that matters, and that itself is regulated by the interstellar radiation field. And I agree that if we made a proxy for the H2 mass and calculated the H2 depletion time in these galaxies, we might get something much more in line with, the standard 2 gig year.
Is it the chicken or the egg question? I mean, about which came first, and if the dust is regulating the molecular content, and the lack of dust in dwarfs is combined with the interstellar radiation seems to, I guess I'm just not convinced about which effect is
Sure. Well, you mean which part of the interstellar radiation's effect is coming first, or which between these two?
Well, maybe we can talk.
Yeah. Yes.
So during your talk, I was thinking of the recombination effects, and in answer to Avi's question, you said self-shielding might become important. I mean, along the lines that I was thinking. So did you try different densities, even if it was over a relatively narrow range? And do you have a prediction for how this depletion time would change with the galaxy mass? I mean, even if you're not including it now, you could at least estimate when self-shielding is and when recombinations are important, and maybe
Yeah, we haven't done an explicit estimate of where self-shielding kicks in. In terms of, strictly speaking, density of the galaxy, we can change the scale length of the galaxy, and that does affect the depletion time as well.
Does it affect your conclusion, though, of which one is important?
No, not as far as I can tell.
Thank you very much.
Thanks.
So, completed it already. I'll try again. Go again. And try again. No. It's- I think I'll try with that. Okay. Yeah. Okay.
Okay. You want to present?
Microphone, please.
Microphone. Okay, can anybody hear me? Okay. Detecting pulsars in tight binary systems. So I'm Barak Zackay from Weizmann Institute in Israel. My advisors are Eran Ofek and Avishai Galian. Motivation for finding binary pulsars, or pulsars in tight binary systems, is tests of GR. Our best tests of GR comes from these systems. It's very important to find them. There's a problem. It's very hard. Why is it very hard? Pulsars are faint intrinsically, so you need long, long integrations even with the largest telescope. Okay, but there's a catch. You have to know the fine details of the binary orbit prior to detection, which is kind of an oxymoron. Right now, the status is that this is considered impossible at maximal sensitivity. The current approach is that the orbital motion is approximated as a uniform acceleration along the line of sight from us to the pulsar, okay, which is not a Keplerian orbit. Okay? But if you look on time intervals which are short enough with respect to the orbital period, then this is approximately correct. Okay, sometimes they add another derivative, which is the jerk derivative. Now, this is extremely computing intensive. Even this is extremely computing intensive because analyzing radio data that gets to you with gigabytes per second, and then go to many, many, many acceleration trials and many, many, many dispersion measure trials, that's challenging. Okay? So currently, the state-of-the-art project, whenever they can, use the Einstein at Home system, which is one of the largest clusters of computers. Those are volunteers volunteering the screensaver of their computer to chase pulsars. Okay? That's the current state of the art. Now, this seems like a dead end to improve algorithmically. Why is that? If you want very, very short observations, T-obs, smaller than 1% of the orbital period, then you can do just regular search for periodic intensity. So if you have 1 hour of observation, this means that the orbital period should be quite long, like 10 days. Acceleration search, the state of the art, takes you to 3% of the orbital period. So if we talk about testing GR, we want pulsars which are shorter than 2 hours of orbit. Shorter than 2 hours of orbit means, well, a few minutes. Let's say 10 minutes. Okay? If you want to add another acceleration, this costs you t to the power 6. So as you prolong the observation time, the computation time simply explodes. So this is the best you can do. And continuing from on, it gets worse and worse, worse, worse. Okay? And the current search techniques are already optimal. They already generate a result per log n computation time. So they really demodulate the signal, FFT, and test all the periods at the same time. It's really hard to improve this. So my approach was, first, can we apply fast folding? So the resolution in all parameters increase with the observation time. So if you increase the observation time, you need finer accelerations, finer periods, and finer jerks, and finer whatever parameter is in the system. But the thing that goes for you, if I have 2 pieces of the data, and I already calculated all the relevant folds here and all the relevant folds here, I can generate all the relevant folds in the entire data set just by 1 addition per result. Okay? More details in the talk tomorrow. I'll be much slower on this. Okay? So this improves by a factor of 200. Now, 200 is very good. If you scale to Einstein at Home systems, 200 is very good. But remember, the t to the 6th power, this doesn't give you that much of an edge. Okay? It's not that much of an edge. So how do you carry on to the complete Keplerian orbit? So you need to improve by additional 10 to the 20. So how do you do something like this? Okay, so let's start with something very subtle. The sheer amount of orbits that you need to scan in the demodulation is very high, of the order of 10 to the 20. Okay? This sheer amount of orbit requires a significant result to be larger than SNR of, let's say, 12. Okay? Now, if you just say SNR of 12, what does it mean of, let's say, a chunk which is 1% of the observation time? It means a signal-to-noise ratio of 1.4. Now, with signal-to-noise ratio of 1.4, you cannot make a positive detection by any means. Okay? But you can cross out negative options. So here you have 2 distributions. For the correct option of a period and acceleration, the statistical score that you measure distributes with the blue distribution. For any other random option, you have the red distribution. Okay? Now, let's say that I want to find with high probability the pulsar. I don't want to be 100% complete. Let's say that I'm willing at the first step to give up 30% of the options. Okay? So I can, from here and left, I can say, all the options with score less than 0, you know what? I don't want them anymore. Okay? So I saved 50% of the time, but then I crossed 30% of the correct options. So let's make it extreme. So let's make it in stages. At the first stage, I can't move. I can move. At the first stage, okay, so we have all the options until 1% of the data. Then, here is 1% of the data. Then, we cross many options that doesn't have a score which is high enough. Then, each of these options need to split. Why does it look like splitting? Because all the resolutions get finer and finer. So, formally, each option here is an interval in phase space that it represents. Okay, and this interval in phase space gets shrunk. So it's shrunk to be here and here. But now I have an additional piece of information, so I can make another decision. I have enough information to make another decision. So I cross out more options. So I have here two competing processes. The expansion, which is t to the 3, t to the 6, let's say after a few steps t to the 6, and after a few more steps t to the 10, so it's a violent expansion. But I also have elimination. Now, because elimination is an exponential process, so information comes linear in time, so every binary decision that I make crosses half of the phase space. So you have exponential elimination competing with polynomial expansion. And we already know who wins, and that's the exponential elimination. So for a fixed t to the k of this problem, this saves 100 to the power k divided by k factorial. So let's use the t to the 6 there. That's quite a lot. For a Keplerian orbit, I can already tell you it saves about 10 to the 15 to 10 to the 20 order in computation time. Now, a computation that I do with this computer now, 15 minutes, okay, will take, using all the computers on the Earth, a Hubble time with the past algorithms. So it's really a game changer. It's a game changer in sensitivity because now you can actually analyze large sets of data. You can analyze hours and hours of observation, longer than Keplerian orbits. You can do this in maximal sensitivity, and you can do it on past data. One additional thing is that this applies also to two other problems, which are, if you want, the IPTA, the International Pulsar Timing Array, wants to find as many millisecond pulsars as possible to detect gravity waves in the nanohertz regime. So they want many millisecond pulsars, and Fermi is now 9 years in space, and searching for pulsars using Fermi is also very challenging computationally. Will not tell you why, but believe me on that. There was also a compromise which is of an order of magnitude in sensitivity. It's applicable also to this and to LIGO data for the same problem. Good. It already works on real data. Okay? So I took the double pulsar found in 2005, and I took real data of it that dispersed correctly, and I amplified the noise by a factor of 6. So I have also the truth, and I can give my algorithm a tryout at maximal sensitivity, at the most challenging situation in which the pulsar is just above the signal-to-noise ratio required for discovery. And it already works. So if I plot on the unnoised data, if I plot the best period per bin of time, then I get the blue curve, and the reconstructed parameter set that I have at the end of the pruning process is the green curve. Okay? It works on real data beautifully, programmed now, works on a laptop. Okay? So before we get to the questions, I'll tell you that tomorrow I'm giving an SMA seminar, and I have other radio talks, so if you are interested in finding fast radio bursts, come. And also, if you are interested in finding microsecond long pulses, that's a new thing. I'm opening a new phase space. I'm opening for discovery. And two other works in progress you could see. Also, if you are interested in optical works, so I have optical algorithms for addition and subtraction. In coaddition, essentially, you can take thousands of images of the same part of the sky, summarize them in one image, and be optimal for all science cases. Come talk to me if you want that. Image subtraction. Whoever of you who have done image subtraction knows how difficult it is. This is a first optimal and robust solution for detecting transients. If you are interested, come talk to me. I have an office at P352. Any questions?
So in your test where you added noise onto the double pulsar and then recovered it, that was gouging noise that you added on top of the real signal?
Yes.
In reality, you might expect the noise sources might be more pathological than simply gouging noise.
True.
If you have a lot of pruning going on, you can imagine that if one of the given steps of the pruning, there's some pathological issue that leads to 100% rejection, then it might be difficult to recover a unknown pulsar in this way.
True. So you have to be careful. So I have a way to get around that. First of all, non-Gaussianity is point-wise non-Gaussianity could not bother you because you add so many signals. So the non-Gaussianity that you talk about is actually radio frequency interference that plague every radio observation. And so, for example, if this part of the observation is plagued by radio frequency interference, that could be problematic. But the important part is that, on average, the amount of information you get is constant. And this is true for even if this part is unusable. And if something have been unusable, but I cannot see it from one, fold and seeing that this fold is plagued by some, I have one bin which is too high or something like this. Then if I cannot recognize it point-wise, it cannot interfere with pruning. So essentially, sigma clipping before pruning solves this problem. Any other questions?
Okay, I'm sorry for the technical problem, and thank you very much for the opportunity. Thank you very much for the opportunity to present Bingo project in this venue. Bingo, that stands for Baryonic Acoustic Oscillation from Integrated Neutral Gas Observation. It's a novel experiment, and it was designed with the specific aim to do H1 intensity mapping at low redshift. And it's a project in which we have been working for the past 3 years. I'm going to be giving a talk in SMA in which I will go through the technicalities, and it will be an hour talk. And today I'm going to be happy if you just take away that Bingo experiment exists, that Bingo experiment is funded, it's underway, and our results we are expecting, to be commissioning like next year, and that we are expecting to have some result in the next 3-4 years. Bingo experiment is led by the University of Manchester. It's one of the main nodes, and has been founded by FAPESP, like 75% of it. FAPESP, I would say that is like the NSF of Brazil. And I'm going to present like the different nodes and the different people involved. So as I said, it's led by the University of Manchester, and there are like other several nodes in the UK. The PIs are Ian Brown and Clive Dickinson, are the persons behind the curtains of the whole project. Then money is mainly coming from Brazil, as I said before, from FAPESP, that is their national agency. It's going to be located in Uruguay, and this is particularly important for me because it's my home country, and this is going to make a huge difference, like a 2 or 3 orders of magnitude difference in the development of astronomy in my home country. The PI there is Gonzalo Tancredi. Well, I'm involved, of course, in the project too. And from CFA and Whipple Observatory, Emilio Falco, that works also, we are like a lensing group, is also involved in the project. And then other of the nodes, it's in Switzerland, South Africa, and France. This slide here doesn't make justice to all the people that is involved, to all the different roles that everyone is taking. And yes, and as I said, I'm going to be giving another talk at SMA in which I will go through the whole details. I told you it's going to be located in Uruguay, latitude 35 south. Why there? We actually don't know very well, but I'm happy that it's happening there. Probably we're going to have like very low noise. I think that because of the PI we have worked in lensing before, he had the idea that it would be a good place to put it, and we went ahead with the project. And it's going to be located in that yellow stars that I have pointed there in the northeast of the country, close to a town close Minas de Corrales, and it's going to be located in a quarry. That is an old and unused mine that is called Castrichon. So, I'm going to talk a little bit about the initial concept of bingo, but before I'm going to tell you why this is important, right? I mean, I'm pretty sure that you know. Well, the thing is that one of the most exciting things that we are studying and that we are interested in is how the inhomogeneities that were created after the Big Bang, they transform into the inhomogeneities that we, in the clumping of the galaxies and the large structure that we are observing today. And so those oscillations that are observed in CMB are currently observed in the matter today, as how the different galaxies clump, and that is baryonic acoustic oscillations. And if we measure the scale of the baryonic acoustic oscillations, we actually can measure distances, and if we measure distance as a function of redshift, we can put constraints on the cosmological parameter. So our project wants to measure BAOs at low redshift, and the whole concept was based on this, specifically with these probes. The original concept was to make a little Arecibo in a quarry, as this, artistic 3D model shows. But the thing is that to have the resolution what we wanted, the resolution what we need to do the measurements, we couldn't find a deep enough quarry in Uruguay to do the construction, that it required like almost 100-meter depth quarry. So we have to change. We prefer to change the design instead of do any other changes. And so instead of being a single dish, it was transformed into two mirrors that we call, we call it like the dual mirror design. And now, we found the appropriate quarry in which one of the receivers, the feed horns, are going to be located on which it will be like the left of that figure. The primary mirror is going to be the one that is like of the order of 50 meters, and the secondary mirror is going to be the one that is vertically, and the whole structure is going to be supported by the quarry itself. So here we have a 3D image of how it would look like, and based on the simulations that we have made, for all the properties that we need to do this kind of measurements, the thing is that we need a dish with a diameter of 40 meters. We are forecasting, that we are going to achieve a resolution of 0.67 degrees. The redshift range, I already mentioned that in my first slide. It's going to be a low redshift, 0.12 to 0.48, and the frequency range, you have it there, from 960 to 1260 megahertz. Then, details of the actual telescope is going to have between 50 and 100 feed horns. the size, the temperature that we're expecting, the frequency channel in which we will be operating, and the sky coverage that is, estimated that is going to be of 5,000 square degrees. And the concept behind Bingo, it was that it has to be simple. There are other projects that plan to be doing H1 intensity mapping with interferometry, but the thing of having a single dish first makes the projects really cheap, and the structure is going to be fixed. There are not going to be moving parts or anything. So a very simple concept that is going to be doing state-of-the-art science in a few years, and it's going to be the Pathfinder for SQA. So here we have, I already mentioned all this. There are very diverse goals that we are going to have. The main one, measuring baryonic acoustic oscillations at low redshift. The thing is that also from the power spectrum, you can measure neutrino masses. You can also, you can also do redshift space distortions and maybe test different models, of modified gravity. You can also do a cross-correlation with optical and redshift surveys. And for example, we are planning that it's going to be an overlap of 800 square degrees with the dark energy survey. We can also study fast radio bursts, and this is going to be really very important because up to now, I think that of the order of 20 are known, and actually with Bingo, we are expecting to measure of the order of 100 per year, and Bingo experiment will also cross the galactic plane, so we can also do some galactic science with the data that we are going to obtain. So after all the issues, the thing that I really want you to take away is that Bingo is happening, that Bingo cost is very cheap, that is 4M, and actually is already funded to 75%. It's undergoing, that we are going to do extremely good science. I won't go through I can mention some numbers, but we're expecting to measure baryonic acoustic oscillations to 2%, and we are expecting to improve the accuracy in the dark energy equation of the state parameter omega up to 4, in four times better. Then, phase 1, as you know, is underway. Phase 2, the construction is going to start next year. Once again, it's going to be in Uruguay. We also have a very awesome outreach program that we hope that works very well. And the operations will start in 2018. Sadly, we were expecting this to happen before, but sadly, because of funding, it has been delayed a little bit. And then, as I said, it's going to be the Pathfinder for SQA, because actually, SQA in phase 1 plans to do baryonic acoustic oscillations using some of the dishes. And actually, we are going to have better resolution. So, yes, take away that it's a competitive project. Take away that, that beyond the experiments that I'm pretty sure that you know very well, this one exists, is founded, and is happening. And thank you very much, and I'm sorry for the mess at the beginning.
I would assume with the frequency range that you have, you might also be able to do reionization through helium-2. Have you guys thought at all about that?
Yes. There are other science that we may be planning, but yes.
I look forward to the SMA talk with all the details, but could you do this on Arecibo or the new FAST telescope in China?
I mean,
those are
it
huge
probably.
apertures.
Yes, of course. But the thing is that, we're expecting to do much faster than them. And second, we are going to do this at a different redshift. This is the first time that actually is going to be done in radio. The first time that we are planning to detect baryonic acoustic oscillations in radio. And yes, the thing is having something else at a different redshift and having something else to compare with.
It's also in the Southern Hemisphere.
Yes.
Okay, but if there are no more questions, that's it for us. Thank you.
I said 2 parts, right?
No,
Okay.